So first problem I will do on this Kepler problem. I hope everybody is familiar with the Kepler problem. Attractive or repulsive inverse square force. So this is a question which came in CSIR net 2018. So in the attractive Kepler problem, described by the central potential VR is equal to minus K by R, where this K is greater than 0, some constant. A particle of mass m with a non-zero angular momentum can never reach the center due to the centrifugal barrier. Obviously, everybody knows this centrifugal barrier. How much is this centrifugal barrier potential? What is the centrifugal potential in the Kepler problem? Who can say? Everybody has done the Kepler problem, right? So what is the value of the centrifugal potential in terms of L, the angular momentum?
L into L plus.
Yes, please. How much is it?
Sir, I'm not sure, sir. L into L plus 1 by x.
So what it is directly proportional to R to the power what power? The centrifugal potential.
R power minus 2.
R to the power minus 4.
Minus 2.
Minus 2. Minus 2. Okay. So it is R to the power minus 2. So in this centrifugal barrier, just a minute. The particle, so let's say this is the center of the force. Let's say this is a star and this is a planet which is orbiting around the star, or it's a gravitating body. So the center, the planet can only reach the center if it is no angular momentum. So basically, if the angular momentum is 0, that is the planet is just static, it will come and drop to the this returns to the central body, the central, I mean, gravitating body. But now the question is a different. Not grabbing. The question says, if we modify this potential to VR equals to minus K by R minus beta by R cube, where beta is also greater than 0, something. One finds that there is a critical value of the angular momentum below which there is no centrifugal barrier. Very strange. What is this value? So critical angular momentum LC. This value of LC is what? This came in CSIR net 2080. So how will you do this problem? Let me see. How much classical mechanics have you done? So if the potential is changed to VR is equal to minus K by R to VR is equal to minus K by R minus beta by R cube, then there is a critical angular momentum LC below which there is no centrifugal barrier. How will you do this problem? Can anybody tell me? How will you handle this problem? Anybody can just help with the starting? Who can help? How do you say that whether in one potential VR, some function of R, how will you say that this potential, how will you calculate the radius at which there is a stable orbit?
Differentiate with respect to R.
Yes,
Differentiate with respect to R.
differentiate with respect to R. So the first thing is the total potential V effective R is L square by 2mR square. This is the centrifugal potential minus K by R minus beta by R cube. In the normal Kepler problem, this was L square by 2mR square minus K by R. But here, this another term came, which is by beta by r cube minus beta by r. So how do you do? You have to differentiate with respect to r. So if you differentiate with respect to r, you will get dV effective r dr equals to 0. That is the minimum of the potential. That is a stable orbit. Everybody got it? dV effective r dr equals to 0 is the stable orbit. Can everybody understand this? There is no force, no net force. So centrifugal force and gravitational force are exactly cancelling each other, and the planet is moving around the star in a stable orbit. So here, if you differentiate and put it equal to 0, what are the values of r you get? So this is minus L square by mr cube plus k by r square plus 3 beta by r to the power 4 equal to 0. So if r is not equal to 0, r cannot be 0. Otherwise, it cannot orbit. So you can cancel out r. So here it is r. This is r square. So this comes out to be k plus 3 beta by r square minus L square by mr equal to 0, which implies kr square minus L square r by m plus 3 beta equal to 0. Now you see, this is a quadratic function of r, right? So this will give two values of r. So r equals to L, this is using this rule, L square by m plus minus root over of b square minus 4ac, L to the power 4 by m square minus 12 k beta by 2k. Now you see, for r to be real, this should be greater than 0 under root. So L to the power 4 by m square must be greater than 12 k beta. Therefore, LC is 12 k beta m square whole to the power 1/4. This is your answer. Did you understand the problem? Yes. How did I do it? If you have any doubts, you can just ask. Okay. So, is it clear to everyone? Is it clear?
Sir.
Yeah.
Sir, how you wrote V effective in the first term L square by 2m r square? I didn't get that.
So L square by 2mr square is always your centrifugal term. Right? This L square by 2mr square, it's always your centrifugal term. What is your centrifugal force? Centrifugal force is what?
A force
mv
pointing
square
out.
by r.
Okay.
Right?
Okay.
M omega square r. M v square by r is your centrifugal force, or you can write it to be m omega square r. And your what is your angular momentum? Angular momentum L is mvr, right? Because angular momentum is always perpendicular to the plane of the orbit. Did you get it? So this force
Yes, sir.
is
Yes, sir. I
did you
got it,
get
sir.
this?
Yes,
Yeah.
sir. Yes, sir.
So this effective potential is always L square by 2mr square. L is a constant. So this is m omega square r. So this is basically how you define the orbits. So the best way is whatever the stable orbit is there, you just because there is no net force acting on the particle or planet, this dv effective dr is equal to 0. That means the force, radial force, is 0. Forces are balanced. You see the very interesting thing. If you would have only minus k by r, then what would have been your r? What would have been your r? So V effective r equals to L square by 2mr square minus k by r. So therefore, dV effective r dr is minus L square by mr cube plus 2k by r square, right? No, sorry. Plus k by r square. This is equal to 0. So that means you can have only one value of r. So this is r equals to L square by mk. So this is R0, you can say. So for a stable orbit, circular orbit, you can have R is equal to R0, which is L square by mk. But here, things are rather different. You have a quadratic function of R. And see, the radius will be 0 only when L equals to 0. Because K and M are non-zero. Okay? K and M are non-zero. So this R0, the stable circular orbit radius will be 0. That is, it will just fall at the center only when L is 0. That is, the particle is not orbiting at all. The particle is just flowing head on towards the planet is plunging towards the sun. But here, this is not the case. If L is less than this value, 12k beta m square whole to the power 1 by 4, your particle cannot escape the that gravitating, falling into the gravitating body, whatever be the velocity. Because r doesn't have a real radius, real value. Okay. Did you all get it? It's a very interesting problem. All of you understood how to do this problem? If there is any doubts, you can ask. Yeah. Okay, then I'll start. So this just they gave this question, but this type of problem is called general relativistic Kepler problem. So in general relativity, so this is the Newtonian term, which is minus k by r. The correction to this Newtonian term is minus beta by r cube. The odd powers, there are various corrections. So this Kepler problem is a general relativistic Kepler problem. Okay. So that's a very interesting thing. So now let's go to another question of NET 2080 involving a relativity. So in relativity, there is only few things you should know to remember besides this length contraction, time dilation, and other things, is that the relativistic energy E equals to gamma mc square, where m is the rest mass and gamma is this relativistic correction factor v square by c square. E equals to gamma mc square. This E equal to gamma mc square can be written in terms of P as root over of P square c square plus m square c to the power 4. Gamma m is known as the relativistic mass. I think you all have did this, that gamma mc square must be equal to root over of P square c square plus m square c to the power. And what is P? What is momentum in terms of velocity? How can you write?
MV.
P equals to
MV.
Gamma MB.
gamma mv. So P equals to gamma mv and E equals to gamma mc. Okay. Now, using this, there is a question in the same CSIR to 2018. CSIR NET 2018. This is a relativistic particle of mass m and charge E is moving in a uniform electric field of strength epsilon. Starting from rest, at t equals to 0, how much time will it take to reach the speed c by 2? Will it take to reach the speed c by 2? So, how will you do this? Can anyone tell me the starting point? How will you do this question? So it starts from momentum 0. That is the thing. Rest starting from rest at t equals to 0. How much time will it take to reach the speed c by 2? Half of the speed of light. Can anybody tell? Try.
Sir, F is equal F
Force F.
dp by T. F also equals Q into E.
Q means E. E equals to
MU.
F. So what is F? This force. What is F in terms of momentum or velocity?
So dp by dt.
dp dt. F equals to dp dt. So now then, what do you have to do? Next step. So F equals E equals to dp dt. Right? Then what do you have to do? You need to know the time taken to reach the speed c by 2. How much it is? So when V is equal to c by 2, what is P? When V is equal to c by 2, P is 0.
2 by root 3.
MC by 2.
MC by 2. How did you do? What
Sir,
did
M
I
and
tell you?
2 by root 3 MBC.
Huh?
2 by root
P
3
equals to gamma mv. So this is gamma means 1 by root over of 1 minus c square by 4c square into m into c by 2. So this is mc by root 3. So that means when the particle will reach speed c by 2, its momentum will reach mc by root 3. Therefore, dp dt, so dp by ee equals to dt. Therefore, t is 1 by E epsilon integral dp from 0 to mc by root 3. So which is mc by root 3 e. So A is the correct answer. Okay. See, this is the shortest way you can do. Always remember this formula: E equals to gamma mc square and P equals to gamma mv. So when it will reach the speed c by 2, its momentum will reach mc by root 3, and when it is 0, it is 0. So here, just integrate. dp dt is equal to E, so E epsilon. So T is 1 by E epsilon integral dp from 0 to mc by root 3. So this is mc by root 3 E epsilon. Okay. Everyone understood?
Yes, sir.
Okay. Now, next question is, this is CSIR net June 2011. So this question says the Lagrangian of a particle in applied, writing in short, electromagnetic field is given by L equals to half mv square plus E a vector dot v vector minus E phi. So you know what is A and what is phi. This is the vector potential and this is the scalar potential. So which of the following statements are correct? Which of the following statements is correct? A. The canonically conjugate momentum is P equals to mv. Is it correct? The Hamiltonian is H equals to P square by 2m plus E by m into A vector dot P vector plus E phi. Is this correct? C. L remains unchanged. L means the Lagrangian under a gauge transformation of the potentials. So one option is correct. And D, under a gauge transformation L changes by the total time derivative of a function of some function, of a function of r vector and t. Which of the following is correct? Which of the following is correct? Let me see. How many of you say first one is correct? Is the first one correct?
Incorrect, sir.
Correct.
Not correct, sir.
Not correct. Why? Why P is not MV?
Sir, in this problem, there will be additional terms.
What is the additional term?
P is equal to dou L by dou Q
How
dot Q.
do you determine P?
Dou L
From
by
L.
dou Q dot.
Del L by. So P. So Pi dot. Right? So what is Px? What is Px? Px is del L del x dot. So what is that? What is del L del x dot? How can you do? What is this? What is the Lagrangian in terms of x dot? X dot is Vx only, right? So this is del L del Vx. What is it?
MVX.
MVx only
E A
plus E
AX.
Ax. So Px is MVx plus Eax. Py is MVy plus Eay. And Pz is MVz plus EAZ. Right? So P is not MV. So P is MV plus EA. Right? P is MV plus EA. So this is wrong. This is not correct. This is false. What is the Hamiltonian? How do you calculate Hamiltonian?
Summation PQ dot minus Q.
Pi Qi dot minus L. So if you do Pi Qi dot, so that means Pi Vi minus L. Right? So will you get this? Check. Pi Vi, that means Px Vx plus Py Vy plus Pz Pz minus L. right? So this is P vector dot V vector minus L. So what will you get? Will you get this expression? Try everyone. What is the Hamiltonian of a particle in electromagnetic field? If you know, then you don't have to calculate all these things. What is the Hamiltonian of a particle, charged particle in an electromagnetic field?
Second term will not be there.
This is not correct. Is it coming like this? So how much it is coming? So this is P is mv plus Ea. So mv plus Ea dot V minus L. This is mv square plus Ea vector dot V vector minus half mv square minus Ea vector dot V vector plus E phi. Right? So what is coming? This is not coming P square by 2m plus E by m A vector dot P vector plus E phi. This is not equal to this. Right? This is half mv square plus E phi. Okay. This is not equal to P square by 2m plus E by m A dot P plus E phi. Basically, this is H. So H is P minus Ea whole square by 2m plus E phi. This is the Hamiltonian of a charged particle in an electromagnetic field. Right? This is half mv square plus E phi. So if we expand this, this is not equal to this. So this is P square by 2m plus E square A square by 2m minus 2p 2 E A vector dot P vector by 2m plus E phi. Okay. So this is not this. So this is also not correct. Now, see, L remains unchanged under a gauge transformation of the potentials. What is a gauge transformation? What is a gauge transformation?
Change in potential.
Some other people say, not the same people. What do you mean by gauge transformation of a potential? How do I write a gauge transformation of this scalar and vector potential? You should try. You have done gauge transformation, right? In electromagnetic theory. in your course? What is gauge transformation of these potentials? Have you done? Do you know what is gauge transformation?
Yes, sir.
What is that? Can you
Sir, a
explain?
transformation
What is
that leaves the equations unchanged.
a transformation which leaves the equations unchanged? What equations?
In physically, sir. So the potential equation, the Hamilton, Lagrangian, all that are also.
Lagrangian, does it remain unchanged? So what is the gauge transformation? This, what remains unchanged in a gauge transformation? Lagrangian doesn't remain unchanged, neither the Hamiltonian. What is a gauge transformation?
The physics remains unchanged, sir. I think so.
Physics means what?
So the physical principle that for any global transformations, I'll be getting the same thing.
Global,
somewhat
no, see, global transformation is different and the gauge transformation is different. How these scalar and vector potentials transform into transform under a gauge transformation? If you don't know this, then how will you do the C and D? You have to check what happens to the Lagrangian when this A and phi changes to gauge under gauge transformation. Hmm? Can anyone else say what is a gauge transformation? So a gauge transformation is a transformation of the scalar and vector potentials such that the fields, the electric fields and the magnetic fields remain the same. So the equations of motion will remain the same. The electric field and the magnetic field will remain the same. The main physics is the fields, not the potentials. You transform these potentials for ease of calculations. But the magnetic field and the electric field will be the same. So the magnetic field B is curl of A, right? And the electric field E is what? Minus grad phi minus del A del T. Right? So these are your formulae for the electric and magnetic fields in terms of the scalar and vector potentials. So if you do a gauge transformation, a gauge transformation gives you another set of scalar and vector potentials such that this E and B, the strengths of the electric and magnetic fields, are the same. So this, let us take a function lambda, which is some function of r vector and t, basically x, y, z, t. If you transform this A, that is the vector potential, to a new vector potential, A prime vector is A vector plus gradient of lambda, and transform the phi, that is the scalar potential, by phi minus del lambda del t. So you see that this E and B fields will not change. So this transformation is called a gauge transformation. This transformation is known as the gauge transformation. Okay. So now, what is the new Lagrangian in terms of this gauge transformation? This is half mv square plus E A prime vector dot v vector minus E phi prime. This is equal to half mv square plus E into A plus grad lambda dot v minus E into phi minus del lambda del t. This is equal to the original Lagrangian. I'm taking it out. That is half mv square plus E A vector dot v vector minus E phi. So this is L plus E gradient of lambda into dot v plus E del lambda del t. Now, this you can write it to be L plus gradient of E lambda is a constant dot v plus del del t of E lambda. Now, see, grad of E lambda dot v is plus del del t of E lambda is L plus d dt of E lambda. So how is it coming? So grad of E lambda dot v plus del del t of E lambda is what? Gradient of E lambda dot dr vector dt. V is dr dt plus del del t of E lambda. So this is, what is gradient of E lambda? Gradient of E lambda is what? Del E lambda del x. So this x cap plus del E lambda del y, y cap plus del E lambda del z, z cap. So this, if you dot product with dr vector dt, you will get del E lambda del x into dx dt plus del E lambda del y dy dt. plus del E lambda del Z into dz dt plus del E lambda del T. So if E lambda is a function of x, y, z, t, E lambda is a function of x, y, z, t, then d E lambda dt is yours, this thing, right? Del E lambda del x del dx dt plus del E lambda del y dy dt plus del E lambda del z del dz dt plus del E lambda del t into dt dt, when dt dt is 1. So this is grad of E lambda dot dr dt plus del del t of E lambda. So this Lagrangian under a gauge transformation will be changed by the total derivative, time derivative of a function of r vector and t. So your answer will be D. This is the correct answer. Okay. So all of you, have you understood this problem? Is it fine? If you have doubts, you can ask. The calculations which I have done, is it fine? Okay, so I think it is fine. Or else do I need any clarification on this? Next, like there are some problems I wanted to do regarding small oscillation. Small oscillation problems. Let me do it in the next slide. That's better. Every time this net gives a question, they give a Hamiltonian or a Lagrangian, and they tell you to solve the eigenfrequencies, this or normal frequencies. How do you generally do that? The eigenfrequencies or the normal modes. So you have a potential and you perturb this system from this potential, small perturbation. To find the normal modes, the eigenfrequencies of this oscillation. So here it is in 2050 in net 2050. Every year they give one question on normal modes. So the Lagrangian is given by this half m q1 dot square of a system plus 2m q2 dot square minus k into 5 by 4 q1 square plus 2 q2 square minus 2 q1 q2. So where m and k are greater than 0, positive constants. The frequencies of the normal modes are I hope all of you have done normal modes, small oscillations. Right? All of you have done normal modes? Yes
No,
or
sir.
no?
No, sir.
You have not done normal modes
No, sir. I didn't do that.
yet? Huh?
I don't know, sir. I didn't do that.
Okay. So then before coming, let's see what is this normal modes of oscillation. So how many of you have done the normal modes, small oscillations? And how many of you have done? Can you please raise your hands? How many of you have done the normal modes? I'll just see. You want to check? Can you please raise your hands? What happened? So everybody did normal modes, that means. Nobody did or what?
Done, sir, but don't remember.
Huh? You don't know how to find the normal modes of oscillations of a system? Hmm?
Taking determinant of T something. T.
Okay, how
Right,
many
no,
of you know? How many of you know? Let me see so that I can start. Shall I start from the theory or shall I go in the problem directly? What shall I do?
So better
So
start from the theory. Sir.
better to start. Huh? Okay. So better to start. So this you can well find in Goldstein's book, Normal Modes of Small Oscillations. So let's say you are given a solid or an n-body system joined by springs. So you can have a system which is, a coupled system, you can say. Let's say this is some ball stuck with some spring, and mostly it is sort of an idealized form of the lattice which vibrates at some temperature. So spring, ball and spring system. Okay, this ball and spring system. And each spring has some separate spring constant, K1, K2 or something. And balls will have some different same or different masses, that depends, M1, M2, M3, something. So if now you see, this is a coupled, this goes on. So this system is actually a coupled system which vibrates. So if I put a force on this, then this spring will be compressed and this spring will be elongated. So this will also start vibrating. This will also start vibrating. And if this starts vibrating, then the others will also start vibrating. So this is a very coupled system. So in general, the Hamiltonian or the kinetic energy and potential kinetic energies are functions of the velocities of all the masses. So it's like, so the Hamiltonian is a function of, mostly a function of qi dot qi. Rather, I should say Lagrangian, because Lagrangian contains this qi dot. This is a configuration space. The Hamiltonian I should write in pi. Anyways, that is not the issue. So the Lagrangian consists of mixed terms of qi dot and qi. So how does it go? It is some sort of I'm just telling you a gist. So it is t minus v. So t contains some sort of like this, say half into m into q1 dot q2 dot same one plus some m2 q1 dot square plus m3 into q2 dot q3 dot something, it goes on, plus m4. These are some constants. You can take these constants as mass, but it is not actually mass, I will tell you. But the formula is, the dimension is mass into velocity into velocity. It is mass into velocity square. So m4 into q4 dot square, something like this. So you have not only this m into v, but you have m into v1 into v2 into v2 into v3, and the potential energy is half some constant, say k1 into q1 q2 plus half k2 into q3 square, sorry, q3 square plus half k3 q4 q5. So this potential is also a quadratic form of the form k half k x1 x2 or half k x square. So but the problem is that these terms are mixed terms. They're coupled. They are all coupled with each other. That is very difficult to you know, I mean, for further calculations, it is very difficult to do. So this is the kinetic energy of the whole system, and this is the potential energy of the whole system, and you can find a Lagrangian. So the Lagrangian is a function of qi and qi dots of the form this and this. Okay. So this is the called, I mean, I'm just telling this qi and qi dot is the generalized velocities and qi are the generalized coordinates. Okay. Now, the thing is, you have to find what is known as the eigenfrequencies. These eigenfrequencies are the frequencies in which you have to decouple these masses as individual oscillators. Okay. So basically, what you have done is T is I can write it to be summation summation ij of mij qi dot qj dot, and this V, the potential energy, as summation ij half kij qi qj, where this mij and kij are some constants. What I have written here, some k1, k2, k3, something, some constants are there. Okay. So did you understand up till here? So this is a generalized form of the kinetic energy, and this is the generalized form of the potential energy. Okay. So in this, if you have this thing, sort of, you can write this actually in a matrix form. So what is this matrix form? This matrix form is given as, if qi, say you take it as a column vector, column matrix, q1, q2, to say qn, if there are n number of particles, and qi dots also as this column vector, q1 dot, q2 dot, all these. So this is q1 dot, q2 dot, to qn dot. So you have, this is a vector which contains all the generalized coordinates of the n particle system. And this is a column vector which contains all the generalized velocities of this n particle system. So now the total kinetic energy in terms of these vectors can be written as T equals to half. So I name this vector, this matrix, column matrix, as the Q matrix, and this as the Q dot, the velocity matrix. So you see that this T can be written in a concise form as T is equal to Q dot T M Q dot, and the V can be written as half Q T K Q, where this Q dot T will become a row matrix. This just transpose, you gave it a row matrix, and these two matrices M, this is a 2 by 2 matrix which consists of all the mass terms M11, M12, like that. So these are all the mass terms. This is known as the mass matrix. And K has all the spring constants terms, K11, K12. So this is all Kij's. This is called the spring constant matrix. Spring constant matrix. So the total Lagrangian can be written as half Q dot T MQ minus half QT KQ. Okay. Can you all understand this? because I am not understanding whether you are understanding or not. Can you get this?
Yes, sir.
Okay. So now this is a very interesting thing. This, what is the elements of this mass matrix? The elements of this mass matrix is Mij, right? Elements of this mass matrix is Mij. And elements of this spring constant matrix is Kij. If you make a derivation, so this Mij equals to del 2 L or del 2 T, if you can write del 2 T, del Qi dot, del Qj dot. So if you are given T and if you are given V or if you are given L, also this you can write it to be del 2 L del Qi dot del Qj dot. This is the elements of the mass matrix. These are the elements of the mass matrix, Mij. I should write it as capital. Okay, anyways. So M11 is del 2T del Q1 del Q1 or del 2T del Q1 2. M12 is del 2T del Q1 dot, sorry, del Q1 dot 2. M12 is del 2T del Q1 dot del Q2 dot. M23 is like that. So Mij is del Qi dot del Qj dot equals to del 12 del Qi dot del Qj dot. The spring constant matrix Kij equals to del 2V del Qi del Qj equals to del 2L del Qi del Qj. Okay. So if you want to make the normal modes, you have to find the eigenfrequencies. The eigenfrequencies are those frequencies which satisfies Mij. So, sorry, Kij is equal to omega square Mij. So you got this matrix Mij and you got this matrix Kij. You have to find the now the problem comes to an eigenvalue problem, which is done in mathematical physics. So what now it comes? Here you have, if you take the determinant of this, so this is K minus omega square M equals to 0. This will be some polynomial function of M, some polynomial function of omega in terms of all these spring constants and masses. So you take the determinant of this K minus omega square M equals to 0. Then you will get this eigenvalues. So let's take this problem. Actually, it has this you will learn that this has a lot of other implications. Like this is basically you are doing a principal axis transformation. You are transforming the coordinates in such a way that you are removing these cross terms using this eigenvalues. But I will just what is that problem gone? This is given in this, yeah. previous slide. This one. Lagrangian is half mq1 dot square plus 2mq2 dot square minus k into 5 by 4 q1 square plus 2q2 square minus this term 2k into q1 q2. This is a mixed term. So what you have to do is you have to find this mass matrix and the spring constant matrix. So since there are two particles involved, this q1 and q2 and their velocities q1 dot and q2 dot, this will be a 2 by 2 matrix. So let us do it. So what is the T matrix? Sorry, M matrix. So here M matrix is, I'll just write it. So del 2T, so this is del 2L, del Q1 dot, del Q2 dot. So the first one is del 2L, del Q1 square. What is that? Del Q1, del L, del 2L, del Q1 dot square. So what is that? So this is just M. This is just M. Del 2L, del Q1 dot, del Q2 dot is 0. There are no cross terms in the kinetic energy. Similarly, so the off diagonal terms are 0. M0, 0. This is del 2L, del Q2 dot square. So this is 4M. 0M, 0, 0, 4M is your mass matrix. The spring constant matrix K is given by these derivatives of the potential, double derivatives of the potential. So first will be this 10 by 4 K. So this is 10 by 4 K. So this is del 2L, del Q1, del Q2. So this is 10 by 4 K. This is minus 2K. This is the cross term is there. So this is, yeah. So this is minus, yeah, 10 by 4K. So this is not, this is minus. This is plus 2K. This is also plus 2K. And this one is, this is 4K, minus 4K. Okay. So now you use this secular equation to find this eigenvalues. So you can take out K and M out. So here you have determinant of 10 by 4 minus 10 by 4K minus omega square M minus omega square M. Okay. So this is minus 2k. Sorry, this is 2k. This is 2k. And this is equal to 0. Okay. So now you can have the equation, the polynomial equation. You can just change to this. Okay, I have to make a new slide. Just a minute. Okay, so I just made one mistake here. This mistake is that this should be
0.
What mistake did I do? Can anybody tell? If you are attending, you can tell.
0 will come in 2k. Sir.
Huh?
The 2k will not come, sir. 0.
Why? K minus omega square m. So 2k minus omega square into 0 will be 2k. Right? This is 4m, not omega square m, but omega square into 4m. This is into 4. This is one mistake. Another mistake is del 2v del qi del qj. This is minus del 2l del qi del qj. Because this is L is T minus V. Here it should be a minus sign. Okay. The potential energy is what? The potential energy in this case is 5k by 4 q1 square minus 2k q2 square plus 2k q1 q2. This is T minus V, right? So here signs will be changed. So I should write a minus here. So this is 10k by 4. I'll write it separately. This one. So this should be minus sign. So here it should be minus 2k. I can't edit. I don't know why. This should be minus 2k. This should be minus 2k. This will be plus 4k minus 4 omega square m. And this should be plus 10 by 4k minus omega square m. So your equation will be 10 by 4 10 by 4k minus omega square m into 4k minus 4 omega square m minus 4k square equals to 0. Okay. So this can be written as, so you can cut out 4. So this is 10 by 4k minus omega square m into k minus omega square m minus k square equals to 0. So this is 10 by 4k square minus omega square mk minus 10 by 4 omega square mk plus omega to the power 4m square minus k square equals to 0. So you can make this, it has omega square and omega to the power 4 term. So omega to the power 4m square minus, this is what? 14 by 4, right? 10 by 4 plus 1. So 14 by 4 omega square mk. Again 10 by 4 minus 1. So this is plus 6 by 4 k square equals to 0. So this is 3, this is 7. So this is, can you factorize it? So this will be 2 omega to the power 4 m square minus 7 omega square mk plus 3k square equals to 0. So this you can fact omega square, you can have some value. Omega square. You can do that. I think I ran out of time. This is the polynomial in omega, quadratic function in omega square. So this can be written as, so omega square has two values. So k by 2m and 3k by 2m. Sorry, 3k by m. So therefore omega is root k by 2m and root 3k by m. So these are your required eigenfrequencies. Okay. So the answer is this A, I think. Yeah. Okay. So did you get how to do this type of problem? This comes every year. Find the normal. Sometimes two problems come. Find the normal modes of small oscillation of a system. So in this system has two particles. So it's a 2 by 2 matrix. This mass matrix and the spring constant matrix is 2 by 2. If you have one more variable, Q3 and Q3 dot, then this should be 3 by 3. Okay. So 3 by 3 matrix will be there. But anyways, they will give you so that you can find out the omega square. So these values you can find out easily. Okay. So I think any doubts?